resistor in the back. Hi, I'm Niall Coughlin and I'd like to present to you my master's thesis project for the Sonic Art Research Centre in Queen's University Belfast, and I call these electric chairs. What these are 4 sensor enhanced chairs in the spirit of ubiquitous computing, or augmented objects that have been augmented with technology in order to increase their functionality. So we have 4 fairly standard office or audience chairs. One of the potential future applications for this project is installing in the Sonic Lab in SARC, where all audience chairs might be augmented in this way. What I've done is put 4 sensors into each of the chairs. The chairs are totally passive, they don't require any interaction from the people who sit in them, but once somebody sits in them, they'll start sending data to a Max MSP patch about their occupants. The 4 sensors I've used are 2 pressure sensors, one under either leg. For this we've used a quantum tunneling compound sensor, which essentially detects squashing or deformation of the sensor in any way. In this case, as soon as somebody sits in the chair, their weight pushes down on it, giving a reading into max. I've also put a light-dependent resistor in the back of the chair, which is dependent on the amount of light coming into it, its resistance value changes. This will monitor how far forward the seat somebody is sitting, their posture. And also, the last sensor is a galvanic skin response sensor, which has just been placed on the arm of the chair in sort of a position that their occupant would just, their hand will rest on it naturally. There's also a little elastic band there to hold it in place for more comfortable posture. So these 4 sensors are sending biological data about the chair's occupants via an Arduino microcontroller board to a patch in the computer in Max MSP, which I've developed. And this patch is used to visualize this information. We can see here we have visual readouts of the 4 sensors, the quantum tunneling compound giving us a left and right balance between the 2 legs of the chair. We can also see kind of the angle that somebody's sitting at when we look at the output from the light-dependent resistor. We can also see the galvanic skin response. We can have a reading of this directly from the sensor, and what I've also done is to filter the data, to filter out small changes, which will give a more accurate overall reading. So this GSR sensor is very much like the sort of sensor that we'd see used in lie detectors. It gives an indication of their state of arousal. And what we can do is cross-reference this with the data from the other sensors. We can use it to make a judgment about somebody's emotional state. This is visualized in this part of the patch here, where we can look at the data from all 4 sensors at the same time or individually. Now, what we have here is a very basic form of emotional state sensing. We're trying to gauge people's levels of enjoyment of a piece of music or performance, whether they're nervous, angry, excited, and so on. How I've done this is to use a fairly standard way of graphing emotional state, where one axis is their arousal level, that's the direct feed from the GSR. The other axis is what's called valence, which is an indication of somebody's enjoyment of something or not. And what I've used to gauge this is the output from the 2 quantum tunneling compound sensors, QTCs for short, with the light-dependent resistor, or LDR. And what we're detecting here is if somebody is fidgeting in their seat, if they're perhaps bored. People have a tendency to fidget more. They'll also lean forward in their seat when they're trying to be more attentive. And we can use these as rough indicators of somebody's enjoyment of a piece of music or a performance of some kind. What I've also done is to cross-reference the output from those 2 sensors with the output from the GSR in order to weight that scale, because somebody might well be moving in their seat because they're actually enjoying something. They're moving to a rhythm or something like that, tapping their foot along with a piece of music. And the computer is able to make a judgment of whether they're moving in their seat because they're bored or because they're moving with the beat, based on this weighting from the GSR sensor. All the data from these sensors can be recorded into a text file, which can then be imported into some sort of graphing program such as Excel or MATLAB, in order to have a look at people's responses to a performance over time. The patch also contains an audio input, which allows you to record the piece of music or the sonic art that the audience member, the occupant of the chair, was listening to, and to look at that graph of the readings of the sensors in conjunction with the piece of music. The patch is not just designed to gather data for research purposes, such as the readings from these sensors or the emotional state evaluation part of it. The chairs are also intended as a potential performance tool for composers who are visiting SARC, to allow audience members to have some sort of input into the realization of a piece or the sonification of a piece of audio. A brief performance wasn't carried out using these chairs as part of a showcase of work from the master's show. We can find that in the appendix from the master's. As a performance tool, these chairs would fall into the sort of category of inactive music, where music is generated in real time based on the outputs from the sensors, either an individual chair or the collected data, the interpolated data from all four chairs as a whole, or indeed any combination of individual chairs and the group data. Potential applications for these would be in terms of research of audience reaction to various pieces of music or performances. They also have applications in entertainment, in terms of not just in performance. For instance, if one were playing a computer game based on one of these first-person shooter type games, kill the zombies type thing, more points could be awarded based on how difficult an individual player found a section to complete. We can gauge this using sensors such as the GSR or the other sensors in the chairs, and the player could be more rewarded for completing a passage that they found particularly difficult, perhaps with a greater reward than somebody else who completed the same passage relatively easily. They might also have applications in e-learning, where one might be doing an online training course. Your chair could be monitoring you in real time and detect when your interest levels are flagging, thus prompting the e-learning software to perhaps ask a question or change its approach in the content that it's delivering to you. This could also branch out into things like browsing, online shopping, applications that go on. In terms of where this project might eventually be going, we have the possibility of installing these sensors or a similar system into all the chairs in the Sonic Lab for future performance, and indeed to remain here as a resource for composers and performers. It's increasingly likely that we'll see everyday objects augmented in this way, where they've been enhanced using technology to provide greater functionality to tie in more with computers. I hope this has given you a good overview of the Sensor Chair project. If you have any questions, my email is 2bit@2bitmusic.com.